Welcome to The Explainer. Today, we're going to demystify the invisible magic that powers our entire wireless world: antennas. Seriously, from your phone to your Wi-Fi to satellites in orbit, these things are the unsung heroes of communication. So, let's get into it. You've seen them everywhere, right? The big dish on a roof, the giant tower on a hill, maybe even the tiny little nub on your router. And yeah, they all look wildly different, but their basic job is exactly the same. They are the ultimate translators, turning electrical currents into radio waves and then catching those waves and turning them back into electricity. It's an incredible magic trick. So here's our game plan. We're going to start with the absolute basics, then we'll get into how they actually work. After that, we'll cover how we measure their performance, look at the two foundational designs that started it all, see how they team up in arrays, and then we'll wrap up with a quick recap and a quiz to make sure it all sticks.
Okay, first things first, what even is an antenna? Let's get the big picture right away, because once you get this, everything else we talk about is going to make so much more sense.
So at its very core, an antenna is a special type of conductor. Its job is to be the bridge between a physical wired circuit and the open air. It takes electrical energy from a transmitter and radiates it out into space as an electromagnetic wave. And then, on the other end, it does the exact opposite. It collects that wave from space and converts it back into electrical energy for a receiver. It's the gatekeeper, plain and simple.
All right, so we know what it is. But how does it actually do that? How does it launch energy into space? Because, it's not as simple as just pushing electricity through a wire. There's some really cool physics going on here.
For an antenna to work well, it needs to build up energy before releasing it. Kind of like pulling back the string on a bow before you let the arrow fly. You've got to store that potential energy. So how does an antenna do that with electricity? Well, the secret lies in a concept called resonance. This right here is the key. When you send a signal to an antenna that's the right length for that signal's frequency, something amazing happens. The electrical waves travel to the ends, they reflect back, and they perfectly reinforce each other. This creates what's called a standing wave. It's this perfect resonant state where the energy builds up to its absolute maximum, which lets it radiate out into space super efficiently. Without this, that energy would mostly just turn into heat, and you'd have a very expensive, very useless wire. And check this out. This visual really helps. You can see the standing wave of current and voltage. Notice how the current, the flow of electrons, is at its max right in the middle. That's where all the action is, and that's the point of maximum radiation. But the voltage, on the other hand, is at its highest out of the very ends of the antenna. Getting this relationship is totally fundamental to antenna design. Okay, so antennas radiate, but, how well do they radiate? Just like a car has specs for horsepower and fuel economy, antennas have their own spec sheet that tells us how they perform. Let's look at the big ones. First up is this really cool idea called reciprocity. And this is a huge deal. It basically means that all of an antenna's stats, like its directionality and its gain, are exactly the same whether it's sending a signal or receiving one. And why does that matter? It makes designing and testing antennas way, way simpler. You only have to measure its performance once, and you automatically know how it'll behave doing the opposite job.
And boom, this picture shows it perfectly. Look at the top diagram for a transmitting antenna. See how the signal is strongest coming off the sides? Now, look at the bottom diagram for a receiving antenna. Where does it have the best reception? From those exact same directions. They are perfect mirror images of each other. That's reciprocity in a nutshell.
Next, we've got to talk about direction. An isotropic radiator, that's the one on the left, is really just a theoretical idea. It's a perfect antenna that radiates energy equally in every single direction, like a bare light bulb lighting up a whole room. But in the real world, we almost never want that. We want an anisotropic, or directional, antenna. Think of a flashlight. It takes all that light and focuses it into a powerful beam. That focus is what we call gain. And finally, we have polarization. This just refers to the orientation of the radio wave's electric field as it flies through space, and it's set by the physical orientation of the antenna itself. So a vertical antenna makes a vertically polarized wave, a horizontal one makes a horizontal wave. The critical takeaway here is that the receiving antenna has to be oriented the same way as the transmitting one to catch the signal properly. It's just like trying to fit a specifically shaped key into a lock. So there are thousands of different antenna designs out there. But what's really cool is that almost all of them are just clever variations of two very simple fundamental types. Let's meet the Adam and Eve of the antenna world. First up is the half-wave dipole, also known as a Hertz antenna. This is the absolute building block of antennas. Its most important feature is its length.
It is exactly 1/2 of the wavelength of the frequency it's built for. And that specific length is what allows it to resonate perfectly and create that powerful standing wave we talked about earlier. The second foundational antenna is the Marconi, or quarter wave. And this one is a really clever hack. You take a half-wave antenna, you chop it in half, and you stand it up vertically with the bottom connected to the ground. But wait, how can it work if it's only half the length it needs to be to resonate? Well, here's the trick. A conductive surface, like the ground or the metal body of a car, acts like an electrical mirror. It creates a virtual image of the antenna, which electrically completes the other half. It makes the antenna think it's a full half-wave dipole. And this matters because it lets us build much smaller, much more practical antennas for things like cars, boats, and handheld radios. It's a brilliant piece of engineering. So what happens when you take these basic antennas and you make them work together as a team? You get something called an antenna array. And this is how you get really high performance, way more focused and powerful than any single antenna could be on its own. A perfect example of this is the classic TV antenna you've probably seen on a roof somewhere. It's called a Yagi antenna. It uses one active antenna element and then a few passive ones that aren't even hooked up to anything, but they work together to shape and focus the radio waves into a really concentrated beam. So here's how the team works. In the middle, you have the driven element. That's our basic half-wave dipole, the one that's actually connected to the radio. Behind it, you have the reflector. It's a little bit longer, and it acts like a mirror, catching any energy going backward and bouncing it forward. And then out in front, you have one or more directors. They're a little shorter, and they act like lenses, focusing all that forward energy into a tight, powerful beam. It's teamwork at its best. All right, I know that was a lot of info. So to help make sure all of this really sinks in, we're going to do a quick rapid-fire recap of the key terms, and then I've got a few practice questions for you that you should definitely be able to answer now. Okay, let's run through them. An antenna is a conductor that radiates or collects energy. The standing wave is that resonant state that makes it all work. Reciprocity means its transmit and receive properties are the same. A radiation pattern is either isotropic, like a light bulb, or anisotropic, like a flashlight. Polarization is the wave's orientation. The half wave or hertz is your basic dipole. The quarter wave or Marconi uses the ground as a mirror, and an antenna array combines elements to get higher gain. Got it? Good. Okay, first question for you. Think back to our light bulb and flashlight analogy. What is the fundamental difference between an isotropic and an anisotropic radiator? Next question. What is that principle of reciprocity? And more importantly, why is it such a useful and time-saving concept for engineers? All right, question 3. This one's about that clever engineering hack. Explain how a quarter-wave Marconi antenna uses the ground to perform like a full half-wave antenna. And for our last question, let's think about that antenna teamwork. In a Yagi array, what are the specific jobs of the reflector and the director elements? Thinking through that really solidifies how we can shape and control radio waves to connect our world. All the answers are right here in the explainer, so feel free to rewind if you need a quick refresher. Thanks for watching.